Hi, welcome to our webinar today. This is brought to you by the ASQ Statistics Division. I'm Jenny Hellrung, and I'll be your host today. We have a great speaker with us today. Mike Vella is our speaker. He joins us today following a 42-year career in quality and operations in the automotive and food manufacturing industries. Most recently, Mike retired in 2021 as Senior VP of Operations at the Suter Company, an employee-owned food producer located in Sycamore, Illinois. Prior to joining Suter, Mike was the Vice President and General Manager of TI Automotive's Brake and Fuel Group in North America before retiring in 2006. Mike was with TI Automotive for 30 years. Mike received his MBA from Wayne State University and his BS from Western Michigan University. Mike's been active in the American Society for Quality, serving in the Greater Detroit section and as a liaison to the Automotive Division. He's a senior member and fellow of the Society, and he retains his certification as a quality engineer and reliability engineer. He's also been honored as the Greater Detroit Section Man of the Year. He resides in Aurora, Illinois with his wife, Lynn. While at TI Automotive, Mike and a colleague, Tom Dole, created a week-long training package of statistical and problem-solving methods. Practical problem-solving became a standard for the company's operations and quality teams as process and product development and problem-solving in the group's 35 plants. In today's presentation, Mike will provide a review of hypothesis testing and a few examples of testing for means and for proportions. And just as a couple of housekeeping items, we will be recording this presentation and we'll put it on our YouTube channel later for you to review. We will also have the PowerPoint available on our ASQ website later. Also, you will get an email that gives you the RUs for credit for watching the webinar within the next few days. And if you have questions during the talk, you can put them in the chat, and I will read those out, and Mike will answer those at the end of the presentation. So go ahead and take it away, Mike.
Thank you very much. I'm very much humbled by the invitation to speak to the statistics divisions. I'm not a statistician, I'm just a lowly practitioner. But I really would like to thank Steve Shikula and Jennifer Hellrung for hosting this presentation and inviting me to make this presentation about hypothesis testing. So in manufacturing, it's oftentimes we are involved with process improvements and problem-solving efforts. And this is when we're doing experiments in the process. And it's best for us to use statistically based experiments. So if we want to use statistically based experiments to determine if an experimental change we make on a process actually results in a change in the output. In addition, we want to know which process inputs control a given process output and by how much each process input contributes towards a given result. Point is, what we're trying to know and understand is the difference between fact and opinion. And statistical experiments allow us to know how a process works instead of just thinking how it works. So our agenda today is a quick introduction to hypothesis testing and talking about alternate testing methods, distributions and sampling, performing tests of hypothesis, discussing type 1 and type 2 error, test for means, test for proportions, and just a quick summary. So definition is a statistically valid test of hypothesis, models an observable process and a set of random variables to determine if the process has changed. For example, suppose it is expected that a supplier's new raw material will have a positive effect on production yield. By conducting a test under controlled conditions and evaluating the results using statistical tools, we can state with a specified rate of error that a process either did or did not improve. A test of hypothesis will provide an indication that the results will actually carry over into day-to-day production. So there are other types of non-statistical experimental methods that perhaps you've been involved with on the production floor. Two that come to mind is first is a trial and error, and second is one at a time. Unfortunately, my experience, they certainly lack efficiency. They end up costing way too much and take too long. They're not reliable, and they provide inconsistent results. Let's talk about trial and error experiments. Put yourself on the production floor, and you're down there with the production engineer, perhaps, and the maintenance mechanic and the production operators, and you're going to make a change in the process. Somebody has an idea. We're going to make a change in the process. You're going to try to determine if that change has had a measurable impact on the results. If the desired result has not been achieved, guess what we do? We make another change to the process. The first change may or may not be returned to original setting. We then evaluate the most recent result, and then we continue to tinker with the process, change and test, and evaluate until the desired performance is achieved, if it ever is. So my little picture there with lots of knobs and controls, think of that as a process. Continually mess around with the process until maybe you get a good result. The problem with trial and error is that it can be time-consuming and therefore unnecessarily expensive. Trial and error is absolutely unstructured. There's no guarantee that combinations of variables that you've run are not being repeated, and trial and error results are not reliable because they depend on the experience of the experimenter. Those that favor trial and error often emphasize the trial part and not so much the error part. Another type of experiment is sometimes known as the engineered approach, a one-at-a-time experiment. This is how this goes. First thing you do is you're going to hold all factors constant. That's the premise. You're going to hold all factors constant while changing only one factor at a time. You change it, and then you evaluate the effect. Then you proceed to the next setting or the next factor, and then repeat. And you continue until all the settings, all the factors have been changed to their new level, and all the effects have been evaluated. Well, that sounds great, except for one-at-a-time experiments assume that there's a single golden screw. And all you have to do is find the right setting with the golden screw, and that solution will improve your process output. And success really depends on holding all controls perfectly constant while the experiment proceeds. Now, typically one at a time takes so long that there is absolutely no way in the world you can prove and ensure that all undocumented factors haven't somehow crept into the experiment without the team's knowledge. In addition, one-at-a-time experiments look at factors individually, not in combination with all levels of other factors, and as a result, it's inefficient, it's slow, and expensive. And who's got the time to do that? One-at-a-time is not capable of seeing interaction between factors. So the discussion today is about hypothesis testing. And hypothesis testing is the most straightforward form of statistical experiment. Many other types of statistical methods, such as control charts and design experiments, DOEs, are derived from this basic concept. And the idea, all we're trying to determine with a set of with assumed error is, are they the same or are they different? Has something changed in the experiment? Hypothesis testing is a technique that is used to determine if a change made on a process has produced a significant change on the product. And it looks to answer the question again, are things different? Are they the same? Example, suppose you made a change to a process intended to increase productivity. Great idea. The first month's production figures show an increase or a decrease in output. A test of hypothesis will help you determine if the effect is real or simply a chance occurrence which might reverse itself in the following month. Hypothesis testing can be used to distinguish between performance between different machines, methods, operators, and suppliers. For example, suppose you need to determine whether supplier A or supplier B will provide a similar quality component for, in this case, your injection molding process. A test of hypothesis can provide you direction. Now, those of us who use statistical process control know that process streams exhibit patterns of variation that form distributions. The parameters that we're interested in typically with using statistical process control are the center of the distribution and the width of the distribution as shown to the right. If we draw random samples from a well-mixed population, sample averages will exhibit a distribution of value. Recall the central limit theorem that says sample averages form the normal distribution. That's sort of the heart and soul of statistical process control. Sample averages form the normal distribution. The great thing about knowing that is we know how the normal distribution performs. We know that if you understand the distribution and you have average and a standard deviation, 68% of all the individuals or 68% of all the averages, depending on whether you're talking about individuals or averages, fall between plus or minus 1 standard deviation of the average, 95% plus or minus 2 standard deviation, and literally all 99.73% plus or minus 3 sigma, 3 standard deviations of the averages. Recall that that we're talking about a statistical view of process performance. In this case, the process we've shown here has a center of 8 and a standard deviation of 2. That's a statistical view of a process. Now, and each individual that you pull out of that process is going to fall exactly right on 8. And so when we're evaluating change in a statistical view, we have to ask the question, have one of the process factors changed enough to result in a shift in the process, either forward or behind? We seldom know the true values of the distribution parameters because we don't do 100% inspection of all the items. So we address this question through sampling. So we must decide whether our observed change in our sample statistic in response to a change to the process is due to an actual shift in the parameter or the result of chance. The question becomes, has the process really shifted, or have we simply sampled from a different part of the same distribution? Is it same or is it different? So we can use sample. So how can we use a sample to show if a process parameter has shifted? The answer is we use what we know about random samples and attach probability values to the different results of our sample statistic. Or in this case, we want to diagnose a shift. A sample drawn from the original green distribution on the average will produce a lower estimate of our mean, our X bar, or our average, or sample average, than the sample drawn from the red distribution, the one that's off to the right. The odds of a sample reflected in the overlap are very small in comparison. Using statistical process control, you'll recognize that one of the rules of evaluating control is the 7 points in a row rule. We know that if you see a shift up or a shift down 7 points on one side of the average or other, you know that you've seen a process shift, and that's a change. Well, how about the tails? What if, through the laws of chance, we draw one sample from the lower tail of a distribution and a second sample from the upper tail? What might we conclude? Well, assuming that we have drawn random samples, really the odds of selecting two samples, one that reflects just the lower tail and one that the upper tail, really very small. It's much more likely that both samples will come closer to reflecting the actual mean of the distribution. So that's sort of an introduction. Now I'm going to be talking about the general method of hypothesis testing. Hypothesis testing looks at the odds of arriving at the possible values of a sample statistic for both the original process and the change process. Using this simple test helps us decide whether a given value is more likely to occur under the original set of conditions or the change set. So there are 8 steps that I'm going to go through to performing a test of hypothesis. Step 1. Take a sip of my Gatorade. Thank you. Step 1. Formulate in words the theory or hypothesis that you wish to test. Step 2. State the theory in statistical terms. Step 3. state in statistical terms what conclusion we wish to reach if the theory turns out to be false. That is the alternate hypothesis. Step 4, set a margin of error for the decision. That is, we're going to determine ahead of time the cost or the consequence if we make a wrong decision. Step 5 is to select an appropriate sample size. Step 6, to choose a test statistic and formulate the decision rule. Step 7 is select and measure the samples, actually calculate the test statistic. And then step 8, finally, make the decision based on the criteria which was formed in advance of the test. And this is very important that you set these rules up ahead of the test rather than sort of run and gun during the test. So some terminology and an example. You have some buns there that look like Egg McMuffin buns. So a hypothesis is a proposed explanation for a phenomenon. It's a theory or assumption made about a process parameter. For example, your operations team proposes that if we change to a new, cheaper supplier of baking flour used in our bakery here to make our breakfast buns, we can maintain productivity on the number 2 baking machines at 1,000 buns per minute, but at a lower cost. Sounds like a good idea, right? So again, using some terminology here, the null hypothesis, the HO, this is a hypothesis that we wish to test in statistical terms. A typical statement would read, the HO, or the null hypothesis in this case, is mu equals 1,000. This might mean we wish to test the theory that the process is producing an average of 1,000 buns per minute. The null hypothesis is often known as the innocent hypothesis. Accepting the null hypothesis, the innocent hypothesis, says that nothing has changed, nothing is different. The alternative hypothesis represents our decision, if we have evidence based on our test, that justifies rejecting the null hypothesis. For example, the HA is that mu is not 1,000, or the HA is less than 1,000. Mu is less than 1,000. The process is not averaging 1,000 buns per minute. The process is averaging less than 1,000 buns per minute. When we reject the null hypothesis, it says that something has changed. The process is indeed different. We can also view an inspection process as a test of hypothesis. The null hypothesis in this case is to inspected items conform to specification. That the null hypothesis is that the parts are good. The items inspected are innocent, if you will, until proven guilty. The alternative hypothesis is that the items inspected fail to conform to specification, and when we should reject or rework the parts. So this business of hypothesis tests have always been a bit confusing to me, so I thought I'd state it in the form of a matrix. So let's talk about this inspection process as a matrix. So across the top, parts are good, parts are bad, and then we have inspection results off on the vertical, possible inspection results. We either accept or reject. There's no sort of in between. Either the parts are good or bad. We're going to accept or reject them. So the correct decision is we accept the parts if they're actually good. And another correct decision is that we reject the parts if they're bad. Two other errors is if we accept the parts when they're bad or we reject the parts if they're good. So we call these two types of error, type 1 and type 2 error. On the right-hand side is something called operating characteristic curve, which if you refer back to Mill Standard 105D, is full of these OC curves. Type 1 error, the mistake is the mistake of rejecting the null hypothesis when it is actually true. It's usually noted by alpha, symbol alpha, while type 2 error is a mistake of accepting the null hypothesis when it's actually false, and this is noted as beta error. Alpha error, beta error, type 1 alpha, type 2 beta. So again, back to our error matrix. In reality, if the null hypothesis is true, null hypothesis is false, and our decision rules on the left, we either accept or reject. So if we accept the null hypothesis when it is true, we made a correct decision. And if we reject the null hypothesis when it's false, it's a correct decision. On the other hand, if we reject the null hypothesis when it's really true, we've made a type 1 error. And if we accept the null hypothesis when it's false, it's a type 2 error. So Jennifer mentioned my good friend and colleague Tom Dold. He liked giving this example when we taught this class. It's a story about capital punishment. I don't know how many of you have ever been seated on a jury, but think of yourself on a jury, but not only a jury for some kind of a petty crime, but maybe some big deal where you're sitting in judgment of a person who is accused of murder. Suppose a man has been accused of murder in a state which supports capital punishment. The reality is the man either committed the murder or did not commit the murder. There's no in between. Possible outcomes of the trial are for the accused to be pronounced guilty as charged or not guilty and be released to the public. So turning this into our little matrix, the null hypothesis is the man is innocent of crime. So in our matrix here, if the person did not commit the crime and you as a jury determine them not guilty, you've made a correct decision. You've freed the defendant. On the other hand, if the person actually did commit the crime and the jury found them guilty, again, good decision, okay to execute because this is a capital punishment state. On the other hand, if they did not commit the crime and you actually found the person guilty, that was a bad decision. You're going to execute this person in error, or if they actually committed the crime and you found them not guilty, then you let them off. Bad decision. You release the person in error. So you're on the jury. A type 1 error is made if we reject the null hypothesis of innocent when the null hypothesis is true. A type 1 error would lead us to execute an innocent man. A type 2 error is made when we accept that null hypothesis of innocence when the defendant is, in fact, guilty. You would be releasing a murderer to walk the streets to maybe to kill again. So the question, knowing that errors will always be made, which mistake as a society do we wish to avoid the most? Do we want to avoid a type 2 error or a type 1 error? And how would this decision change if you were in a state that didn't have capital punishment, where that person, if you found them actually guilty and they weren't, went to the state pen and then somehow was able to be, their case was to be able to be resurrected again and somehow let free. This kind of thought process about the type 1 and type 2 error is going to be used in hypothesis testing for determining the appropriate risk of test error. Maybe not as serious as this, life and death, but you've got the concept here. So, in summary of the general method, hypothesis testing is the simplest form of statistical experiment. To use this technique, we must view the decision-making process in statistical terms and determine if a change has occurred. And we make this determination by following the general method of performing a test of hypothesis. And we're going to go through a couple of examples right now. So talk about a test for means. This test is used to determine if some change to a process has caused its mean to shift from its historical value. So you see a little chart on the right, historical value on the left, the green, new process maybe to the right in red. It assumes that we have the previous information about the process mean and standard deviation. In manufacturing, we often don't come into a process fresh and brand new. You have some data, some historical information that tells you how the process has been running. Now, if you don't have historical data, this test is not to be used for this application. You'd use a t-test. For example, The average productivity on our production line over the last 6 months has been 800 units per hour, with a standard deviation of 6 units per hour. Your process improvement team proposes that a raw material change will improve yield. Yay! Although the new material cost is higher, we hope to reduce overall costs by using the new material. Should you recommend the change to management? Some assumptions. The characteristic we're investigating is approximately normally distributed. We're able to take random samples. We know the historic mean and standard deviation, and we can determine that our sample size can be greater than equal to 30 without huge economic hardship or significant disruption to the production schedule. So we're a go for the test. Step 1 is to formulate in words the theory or hypothesis that we wish to test. Our process has been producing an average of 800 pieces per hour over the last 6 months. We propose a change to the process by using a new, more expensive raw material. Can we prove that the extra cost of raw material will be more than offset by an increase in production? That's the question. Step 2 is to state the theory in statistical terms. You have to formulate the innocent hypothesis. In this case, our innocent hypothesis is mu equals 800 pieces an hour. Now, there are other types of hypothesis using greater than or equal, less than, but for simplicity's sake, we're going to use equal for this particular example. Step 3 is to state in statistical terms what conclusions we will reach if the theory turns out to be false. What's the alternative? So we write the alternative hypothesis. Excuse me. Our alternative hypothesis is mu is not 800 pieces an hour. Now, because we don't know if the new process performance will be above or below the historic number, this test is going to be what we call a two-tailed test to explore the possibilities that our change provided for more or less than historic values. Step 4 is to set a margin for error in this decision. The question about error is to determine how serious or expensive are the consequences if we make a wrong decision. Are you going to put your career on the line, or is this just one test among many, and if we make a small error, then we can go back and recover? For simplicity's sake, in this case, we're going to select type 1 error, alpha error of 5%. Step 5 is to select an appropriate sample size. Since our test requires a sample size of at least 30, we'll choose n equals 30. Step 6 is to choose a test statistic and formulate the decision rule. For single sample test of means with a known standard deviation, the test statistic is z equals x bar minus mu divided by sigma over the square root of n. The test statistic, in this test statistic, the x bar is the average of the sample we've drawn from the new process. Mu is a historic process average. Sigma is a historic process standard deviation. And the square root of n is the square root of our sample size, in this case 30. And the null hypothesis, if the null hypothesis is true, the test statistic is distributed as a standard normal with mean 0 and sigma equals 1. We'll view a table of normal probabilities for z equals alpha divided by 2 because we're going to conduct this as a two-tailed test. So we're going to take that 5% error and we're going to split it in two, considering both the possibility of being above or below our mu or our parent distribution. In our case, we're going to look for z equals 0.05 or 5% divided by 2. We're going to be looking for, in our table, factor associated of 0.025, and 1 minus that. We're also going to be looking for a factor that reflects 0.975. So we're going to be looking in the table for 0.25 and 0.975. So to find that z-score equivalent to alpha of 0.025, we're going to look through our table until we find that probability listed. And it's going to be reflected, if you see this curve here, in the left-hand column, we're going to find 1.9. We'll find that in the table in a minute. And we're going to look across the top, and we're going to find that this lines up with 0.06, or a factor is going to be 1.96, and it reflects that tail to the left. So here is a table that I picked off the internet, ASC standard normal distribution table. As I've mentioned, we're going to be looking for 0.025, and I've put a little rectangle there, and it lines up with our factors 1.9 on the left, across the top 1.96. And since this is going to be obviously a symmetrical distribution for the top, we're going to be for the top of the distribution, we're going to be looking for the 0.975, and we'll find it equally as easily by looking in the table, and we'll find it positive 1.96. 1.9 on the left, 0.06 across the top reflects 0.975. So a caution about tables, and this is something that really tripped me up a couple times when I was taking the CQE and the CRE exams back in the 70s and 80s, is that I found myself using different tables, and different publications use different tables because they're calculated different. What I would urge you is that you would use a set of tables, become familiar with how the tables work, and stick with it. You're not switching back and forth, because they might prove to confuse you, as they did me. So selecting our two critical values for this test for a two-tailed type 1 error of 5%, we're going to split that 5% between the two ends of the table, ends of the distribution. In our example, we found that the lower critical value is negative 1.96, and the upper critical value is plus 1.96. So our acceptance region to accept the null hypothesis is to find a z-factor in our calculation that's between negative 1.96 and positive 1.96. And we would reject the null hypothesis if we find z is less than negative 1.96 or greater than positive 1.96. So step 7 is to select the samples from the process and calculate the test statistic. One sample randomly selected from each 30 hours of production were drawn from the new process. Values of mu and sigma were taken from the previous data and simply plugged into our equation. Again, we'll make the decision based on the criteria which was formed in advance of the test. If z is greater than positive 1.96, we're going to reject the null hypothesis. And if z is less than negative 1.96, we'll reject the null hypothesis and conclude that the new process is less than the historical value. So if, on the other hand, if our z value falls between negative 1.96 and positive 1.96, we'll accept the null hypothesis and agree that the process really hasn't changed and the new average is the same as the old average. One more thing that we can state is that when we say that we conclude that the process has really changed, we're really not going to conclude anything. We must say that we have insufficient evidence to support the premise. We never really prove anything with a test of hypothesis because we're simply taking samples, but it gives us a very, very good indication. So again, making our decision rule in a graphic fashion, our acceptance region is there between the red lines, between negative 1.96 and positive 1.96. And if it falls outside that standard normal with a mean 0 and sigma standard deviation of 1, we'll reject the null hypothesis. So completing our example, our old process averaged 800 pieces an hour with a standard deviation of 6. The question is, does the process perform better or worse after our change? Well, we find that after sampling our new process, our sample average is 805 pieces per hour. Can we conclude that things have changed? Have they improved? There'll be people on the floor. That's only 5 more pieces an hour. Is that a big deal or not? On the statistics and find out. So here are the calculations. There's a z formula on the left, 805 divided by 800, x bar minus mu divided by 6, which is the standard deviation, over 5.48, which is the square root of 30, which gives us a result of 4.58. Z is 4.58. Since z 4.58 is greater than 1.96, we say that we reject the null hypothesis, and we say the process has indeed changed. Great news. At the same time, we also say that there's a 5% chance that we made a mistake in our decision. We turn that over to management and we say, okay, it's a good chance that the process has improved, 5% chance of error. How about, I know that we have a number of people from the automotive division. I welcome you that in. I worked for an automotive supply company for 30 years, TI Automotive. And in that process, I was very familiar with evolution and in some cases revolution in terms of coatings on brake tubing that's provided. In this case, we're going to talk about brake tube coatings in North America. On the right-hand side, for you having crawled underneath a car recently, is an example of a brake fuel bundle that provides fuel vapor to go from the fuel tank to the engine. So modern automotive brake and fuel vapor designs require a high level of corrosion resistance from environmental conditions. Over the years, continually aggressive reliability requirements have been met by OEM suppliers, resulting in current day high-performing sacrificial and barrier coatings. Brake and fuel lines these days just don't fail because of corrosion. So I'm going to be talking about a little progression of coatings and talk to you a bit about brake lines. What you see there on the left is a cross-section of the double wrap brazed tube. This product has been in production for almost 100 years now, and it is the industry standard for brake lines. So this low carbon copper brazed tube is made in a number of ways, but it is a very, very inexpensive product, yet it has very, very high performance. Typical automobile under panic conditions, internal brake conditions can produce about 2,500 psi. This tube typically has a bursting point about 10 times that. So it's a great product and has been the standard for automotive applications for many, many decades. Now, the tube by itself is steel, so you have to cover it with some kind of coating to protect it against the environmental conditions. Now, this little table that I've provided is sort of a little sequential history of my experience. Back in the 70s, the tube was coated with something called Tern, T-E-R-N-E, which is a lead tin coating. The tube was pushed through a big hot dip bath, and that provided for a big barrier coat. It worked pretty well, but that product was not sacrificial, and it had many, many little minute, impossible to see voids, and over the years would allow corrosion to get in and corrode the tube. A big advance in the 80s was a zinc-rich primer, which was coated over the Tern. Zinc is a sacrificial coating, and that provided a great improvement for corrosion resistance. Next big step was the introduction of this product called Galfan. Now, Galfan is a trademark product by the Lead Zinc Research Organization, ILSRO. And Galfan is a hot-flowed zinc aluminum coating, which provides even better corrosion resistance than the zinc-rich coating. So that was a great sacrificial coating, but then sort of the big push, the great improvement beyond that, was to have a barrier coat, nylon, which was coated over the Galfan. So now you have an extruded nylon, which is very, very strong and almost impossible to penetrate. I'm not saying completely possible, but very, very difficult to penetrate. And it's over a sacrificial product. And this product, nylon or Galfan, which is sort of the industry standard here in North America, is an outstanding product that is used in pretty much all applications in North America. So in our case, we're going to be talking about a double wall copper-coated steel tube coated with nylon 12 over a zinc-rich aluminum alloy. And in the introduction and development of this product, many, many, many trials went to go on and perfect this process, and I imagine they're going on for a continuous improvement process even today. So as a sort of suggestive of industry standard, we'll talk about the thickness of the nylon coating as determined by cross-section, is targeted at 0.006 millimeters with 0.003 millimeter minimum. Think of that as a sort of a shell around the tubing. Now I have a couple of pictures here, again taken from the internet. So the line description there, considering that perhaps the tube has already been coated with Galfan. Let's say you have a coil of tubing, 5,000 or 10,000 feet, introduced to a payoff. It's uncoiled. The tube is straightened, and then it is heated. And then that thing in the middle, the cone, think about that as an extruder and a die. We're going to extrude nylon. That picture to the right is suggestive of a cross-headed extruder where nylon is forced through a die. These dies here in the center are suggestive of kind of coating dies. And then the coating is applied to the tube evenly, symmetrically, and then the tube is cooled, so the nylon is sort of frozen onto the tube and adheres to the Galfan. Capstan there keeps the line in tension, and then there's a tester to make sure all the splices in the tubing, because it's a continuous process, you don't want to shut it down, are pulled out, and then there's a take up. And then from there, that coil then is taken off to the side and released, and it goes into other processing where the tube is cut to length and fabricated for applications specific to the vehicle. So again, these are examples, illustrate line layout, tooling, extruder are industry typical and selected from internet images. So here's our example. Your process engineering leader claims that the team has developed a new nylon extrusion tooling design they claim will maintain the current process capability for coating thickness while significantly reducing replacement tooling costs. That's a good deal. The current process is an average nylon coating thickness of 0.0064 millimeter with a standard deviation of 0.0008 millimeter. Therefore, the CPK is 1.41. Those of you who are familiar with that calculation, 1.41 says that is a very good CPK. 1.33 would indicate there was at least 3 standard deviations between the center and the lower specification limit. And so 1.41 is a very good CPK. We wish to test the null hypothesis that mu is 0.0064 against the alternative hypothesis that's not. So the team has installed new tooling and agreed to test their hypothesis by taking 25 samples over a single hour's production. Very short snapshot in time. The average thickness we found over the course of the experiment was 0.0066. We've chosen to risk of making a type 1 error as 1%. And so now we're going to ask the question, do you accept the process engineer's proposal? Note that this data is provided is illustrative of production performance, not actual production performance. So we go into our table and we're looking for, so one tail test, and we're looking for the factor there, or the variable that's close to 1%. So we find that in the table in our little rectangle, 0.99010, as close as we can get to 99%, and that lines up with a Z factor of 2.33. Actuality is 2.326, but for our case here, it's 2.33. It's our Z factor. So our null hypothesis is that our HO is 0.0064. Our alternative hypothesis is that it's not. That it's not 0.0064. Our error rate is 1%, and our critical region is the 2.33, what we found in the table. Our sample average is 0.0066. Sample size is 25. So we put that into our test statistic. We find that Z is 1.25. So we find that the calculated Z does not exceed the critical region, and therefore we accept the null hypothesis that nothing has changed. So that's good news. The process has not changed, and the tooling cost is less. Everybody should be happy. So that's ends our discussion about tests for means, but what about tests for proportions? It's sometimes necessary to test the idea that a change has occurred in a process characteristic that is measured by attribute data as opposed to variable data. For example, scrap rates, percent on time shipments, absentee rate, process yield, sorting rate, safety performance. The null hypothesis for this test is that, in this case, P equals P0. In other words, this means that our new proportion of percentage is the same as the traditional value. For example, the percent scrap for the new process is equal to the scrap for the old process. Percentage of on-time shipments is the same as always been. Changing our attendance policy didn't change anything. Yield in our injection molding process is the same since we changed to our new supplier of resin. So the alternative hypothesis is that P is less than PO or P is greater than PO. Example, the scrap rate in our process actually did change. The percentage of on-time shipments increased or decreased after the change as a result of a change in our SOPs, or we have more or less absenteeism than we did before, or our injection molding process got better or worse with a new supplier of resin. The assumptions are that individual trials are independent. This means that the results of one trial has no bearing of the results on the next trial. In addition, the process must be operated randomly. That means that the process must be in the state of control. And our sample size must be large enough so that we would expect to find an average of at least 5 defects in each sample size. So here's an example using ibuprofen. Again, made up example. Arthritis is a painful chronic inflammation of the joints. An experiment proposed on the side effects of pain relievers examined arthritis patients to find the proportion of patients who suffer side effects when using ibuprofen to relieve pain. The point here is that if more than 3% of users indeed suffer side effects, the FDA will make us put stronger warning labels on the packages of ibuprofen. So step 1 is to formulate the hypothesis in non-mathematical terms. Will the FDA require a heightened warning on ibuprofen? Step 2, determine the null hypothesis. In this case, HO equals 0.03, where P is the proportion of users of ibuprofen who suffer side effects. The alternative hypothesis is that P0 is greater than 3%. Step 4, the type 1 error again will be 5%. Step 5, calculate the sample size. In our case, 440 subjects with chronic arthritis were given ibuprofen for pain relief. Step 6 is we're going to write down the test statistic and the decision rule. The decision rule for us is alpha. Our type 1 error is 5%, which we find in the normal table, and we're going to reject if that null hypothesis, if in the normal table we found, which we find to be 1.645, and that's our item in our table. Step 7 is to draw and measure the samples. In this case, 22 subjects suffered from adverse side effects. So our sample proportion is 22 or 23, I got it wrong there, 23 divided by 440, or 5.23%. So we run the numbers through the formula, we find that our Z factor is 2.75. Step 8 is to make the decision based on the criteria which was formed in advance of the test. Since the value of the test statistic, 2.75, is beyond the critical value of 1.65, we must reject the null hypothesis and conclude that there is sufficient evidence that the proportion of ibuprofen users who suffer adverse side effects is greater than 3%. And therefore, the FDA would make us put more serious warnings on the label. Well, let's come to a summary. So, hypothesis tests allow us to determine, again, if an experimental change made on a process results in a change in the output. Hopefully now you can see how understanding how to use hypothesis tests allow us to understand which process inputs actually impact a given process output and by what degree each process input might contribute toward a given result. Again, statistical experiments allow us to know how a process works instead of just thinking that we know how a process works. I'd like to thank the Statistics Division and the Automotive Division for the opportunity to present today. Steve Shikula and Jennifer Hellrung, thank you very much. I'd like to thank my teachers, especially Dr. Hans Majeria of the Detroit Section ASQC for introducing me to hypothesis testing during my CQE prep back in 1978. Mr. Tom Dold, my longtime and valued colleague at TI Automotive, for his enduring work and training and continuous improvement, and for the ASTM for the images of the double wall brake tubing. Jennifer?
Thanks for that. That was very interesting. There was a question that came up during the talk. How do you get the sample size for testing?
Well, you take as many samples as you can, but it need to be at least 30 to make a rational kind of sample size.
Thank you. Just check.
And if you recall, in the test for proportions, I put in sort of a rule of thumb is that you have to have the sample size large enough that you'd expect to find 5 defects in every subgroup. So the little formula that I use is the sample size is 5 divided by P bar, the average fraction defective, and that'll give you a sort of a rule of thumb for sample size.
Great. I think that's the only question we had, and that was a great webinar. I think we can end for today. As I mentioned, you will get an email for documentation of the certification credits, and I will be posting in the email. I'll tell you the links for where everything will be posted. So I just wanted to thank Mike Vella again for that great presentation, and I hope to see you in another webinar in the future.
Thank you all.